Okay, so we've heard how the stellar properties of galaxies and their satellites can inform the physical processes underlying quenching. But I think that it's difficult to discuss quenching without considering the gaseous halos that surround galaxies. This so-called circumgalactic gas is bound to the dark matter halo. It is where accreting gas meets galaxy-scale winds. It's the medium through which all inflowing and outflowing gas must pass. And therefore, its size, its structure, its composition are intimately tied to the history and the future of the galaxy residing at the center of the dark matter halo. I think that the physics that govern the circumgalactic medium must be inextricably linked to the physics that govern quenching. If it's a lack of cool gas flows that terminate star formation in galaxies, then I think the CGM would presumably reflect this. If the interstellar material of quiescent galaxies is rapidly ejected from the galaxies themselves, then the circumgalactic gas would presumably reflect this. And if there's some mechanism that keeps galaxies from forming stars, preventing gas from accreting onto galaxies, the CGM could reflect this. I think by now we all know that galaxies quench. What I've come to understand is meant by this term is that galaxies transition from a blue cloud to a red sequence, and perhaps they stay there, perhaps not, and there are different mechanisms governing whether they stay there. I thought Joanna provided an excellent review of some of the theory behind quenching and potentially maintaining a galaxy's lack of star formation. So I will just tell you the commonality that I find among all of these methods for quenching is a lack of availability of fuel for star formation. In some cases, you have what's effectively fuel exhaustion. You have fuel removal. Or new to me is this idea that the fuel is paralyzed and therefore unavailable to form stars. But I think because the definition of quenching is that galaxies are no longer forming a significant amount of stars, and stars are formed by gas, then it makes sense that you might want to follow the gas and invoke some theory that involves something that happened to the gas. And so people have done this, and I think very impressively, within early type galaxies have found that 40% of early type galaxies have between 10 to the 7 and 10 to the 10 solar masses of H1. And they also, not an insignificant fraction of early type galaxies, 22%, seem to exhibit detectable molecular gas. And so this complicates our picture of quenching. I think, at least from the last conference I went to, they seemed to conclude that the gas inside of quenched galaxies is more of a signal that they're regenerating, and so a failure of whatever is maintaining a quenched nature of a galaxy. But I don't think people have given adequate consideration to the gas outside of quenched galaxies, and indeed what that actually means as far as quenching theory is concerned. And so in this talk, I'm going to summarize 3 main observational results from a survey that I've spent the last 4 years of my life working on, which is COS halos. And in particular, I'm going to stress the 3 results that all L-star galaxies at redshift 0, including quiescent galaxies, show significant H1 absorption in other cool metallic ions out to 150 kiloparsecs. This gas is bound to the halo. The cool, approximately 10 to the 4 Kelvin gas, the cool gas is highly ionized and metal enriched, and there's enough of it to account for more than 50% of the baryon budget of a Milky Way-sized galaxy. And the blue-red dichotomy seen in the galaxy population is reflected by the strong presence of oxygen-6 around star-forming galaxies and its absence around non-star-forming galaxies. And the main point of this whole talk, so you can, I guess, stop listening now if you want, is that it seems most models of quenching and quiescence are tuned to keep gas from cooling onto a galaxy. But we have found, however, that cool gas abounds in the halos of galaxies. And so I think that any successful model of quenching needs to account for this abundance of cool gas around galaxies. I mentioned that I am working with the COS Halos team, which is systematically surveying the halo gas of galaxies. What we do is we carefully select quasar galaxy pairs in the night sky. We select them knowing the galaxy redshift to these sight lines to lie within 150 kiloparsecs of the galaxy disk. We selected the sample specifically to include both quiescent and star-forming galaxies. We have 16 quiescent galaxies, 28 star-forming galaxies that comprise our L-star, roughly L-star galaxy sample with an average halo mass of 10 to the 12.2, and they're at a redshift of approximately all 0.2. Okay, so what do we see when we look at the gas within 150 kiloparsecs of a galaxy disk? And you can see here, I'm just going to show you a few postage stamps. They're not meant to impress you. Quasar, some smudge of a galaxy at redshift 0.2 from the SDSS survey. And based on a very accurate and precise systemic redshift of the galaxy, which we get with Keck optical spectroscopy, we can then go and hunt for absorption at that exact redshift along in the spectrum of the quasar, along the sightline to the quasar, in this case 15 kiloparsecs from the galaxy. And I'm just going to show you some Lyman alpha absorption from these cosmic origin spectrograph data. And so here's one example. Okay, again, this one's a little further, 60 kiloparsecs. We go hunting for Lyman alpha, and there it is. Okay, in this example here, again, we're at 34 kiloparsecs. We go hunting for Lyman alpha. 88 kiloparsecs, galaxy redshift. This looks like a more quiescent galaxy even. And we have absorption. So if you summarize this all in one plot, you can put the equivalent width of Lyman alpha on the y-axis. This is the distance from the galaxy, the projected distance from the galaxy, impact parameter in kiloparsecs. Red galaxies are given by the red diamonds, blue galaxies by the blue squares. And you can see that both red and blue galaxies alike show significant absorption with a very high covering fraction. This is 90 plus or minus 5% above a column density of 10 to the 15 atoms per centimeter squared. This is a very, very high covering fraction. It's almost consistent with 100% when you consider massive galaxies, 150 kiloparsecs. So I think the conclusion to draw from this is that there's no obvious suppression of cool gas around massive quiescent galaxies. Now, this plot is just to emphasize that the galaxies have metals. I'm showing you here a transition silicon-3, which is well covered by the COS Halos data set. And you can see that there's very high covering fractions of metals. There seems to be a decline with impact parameter, now abbreviating that row, but that there's no significant difference between the red and the blue galaxies in terms of their low ionization state metal lines. So red and blue galaxies alike are surrounded by metal-enriched cool gas. And okay, so maybe I've given this talk too many times or some version of it, and I'm constantly faced with questions along these lines. And so here are the three most common arguments of CGM deniers, especially the ones that don't like the idea of cool gas around the red galaxies. In the first case, you can invoke the intergroup medium. But no, actually that's not the case. I can refer you to Jason Tumlinson's 2013 paper where he did a more extensive analysis of this and modeling of it. But the gas is within our veer of the central galaxy. In COS Halos, we selected galaxies specifically to be fairly isolated. The gas is bound with a very high covering fraction, which is very, very hard to reproduce in the case of an intergroup medium. Are we seeing satellite galaxies, strip material from satellite galaxies? The numbers just simply are not consistent with that picture. The projected area and kinematic widths of the absorption in the data are not sufficient. There are multiple components per line of sight, all of which are clustered in a small region of velocity space that is really not consistent with what you would expect for satellite galaxies, which would be fewer than one per sight line. So, and then, of course, maybe we just have a small sample of red galaxies and, I don't know, we're just wrong somehow. We've associated the wrong galaxy and there's really a blue galaxy there. But in fact, there's cool gas around galaxies and other studies, and in particular, I'm highlighting this excellent work by Guangtan Zhu, where he's taken SDSS data and looked around luminous red galaxies at redshift 5 for signatures of magnesium-2 absorption, and he finds a huge amount of magnesium-2 absorption around luminous red galaxies. And so this is not an abnormality from our data set. So I think that this abundance of cool gas directly challenges theory. In particular, in a picture where halos are quenched above a specific mass, Kyle Stewart has done some work where he predicts that the circumgalactic cool gas around these quenched galaxies will drop precipitously at this particular mass. And he actually has a plot of the expected covering fractions of H1. And so this is for accreting gas, but you can see here, the cos-halos result is that within 160 kiloparsecs, we get a covering fraction of 90 plus or minus 5%. This is at a halo mass of about 10 to the 12.2, so right here. And in all of these cases, the gas has dropped to effectively 0, and the covering fraction within 100 kiloparsecs is quite low. And now, of course, you can invoke maybe the rest of it as winds, but that's an awful lot. And so I think that this result is directly at odds with theory on quenching. And so another question. I'm sorry, yeah, that's a particular simulation, not simulation, but I think it is at odds with others as well. Okay, so you can ask yourself how much gas is actually out there available for star formation. And to do that, you have to perform an ionization correction. Most of the gas is ionized, and so you can do this by cloudy modeling, which I've done, and I can refer you to my paper from 2014. But you can construct a kind of surface density map of a total hydrogen column around a galaxy. And when you do this, you find that there is probably enough material in the circumgalactic medium of galaxies to close the sort of missing baryon problem on galaxy halo size scales. There's more gas in the cool circumgalactic medium, that is at the 10 to the 4 Kelvin circumgalactic medium, than there is in the disk of the galaxy itself. And this is also true for red galaxies. And so what do we see then? So the circumgalactic medium is clearly, at least in the cool gas, not reflecting the dichotomy in blue and red galaxies in the universe. But in fact, we actually probe a higher ionization state transition, oxygen 6, which does seem to reflect this dichotomy. And so Jason Tumlinson in 2011 published a science paper in which he showed that around star-forming galaxies, oxygen 6 absorption is very, very strong. And around red galaxies, it's either absent or very weak, almost consistent with the intergalactic median. And you can look at this and like this, and you can see that there's a clear statistical difference. Whereas in the lower ionization state gas in the H1, you saw no statistical difference, no significant statistical difference. This oxygen 6 absorption tends to be also correlated somehow with the star formation rate of a galaxy. And so this dichotomy of oxygen 6 is actually very interesting and informative in terms of the quenching problem. And I think also any successful theory of quenching would need to take into account this particular observational result. What I think are interesting questions and what I'm currently working on are the following: equilibrium considerations. Will this cool gas drive new star formation? And how does oxygen 6 coexist with the cool gas, and why is it an absent ionization state around quenched galaxies? And I'm running a little short on time, but I would like to show you the two things that I kind of weigh in my head on a regular basis. So this correlation of the galaxy star formation rate actually. The correlation of the galaxy star formation rate with oxygen-6 absorption, this is column density of oxygen-6, star formation rate, is actually increased and a better statistical correlation if you divide by the square of the impact parameter, indicating that maybe indeed the ionizing radiation from the galaxy is having some impact on the oxygen seen in the halos of galaxies. And this is a very statistically significant correlation. I think it's like a Kendall-Tau test rules out the null hypothesis at a 99.9% level. Okay, so, but there's also this idea that oxygen-6 might just, in fact, be a signal of gas accreting. Oxygen-6 is only found around star-forming galaxies, so perhaps it's produced in some kind of dynamic interaction between rapidly cooling gas and its surrounding medium. But maybe star formation itself is producing the oxygen-6 absorption and affecting this. But in either case, I think this dichotomy in oxygen-6 in the halos of galaxies is fairly telling and reflective of this problem. So just to summarize here and drive these points home, all L-star galaxies, including quiescent galaxies, show significant H1 absorption. The gas is bound to the halo and represents a massive reservoir. There's this red-blue dichotomy that's reflected in the presence and absence of oxygen-6. And I think that the existence of this gas and its various ionization stages challenges current models that require gas exhaustion and removal.
Thank you. All right, we have time for some questions. Abhishek.
I have some questions and comments. The main questions that come to mind. How much total mass there is in the cold gas? How much total influx there is in the cold gas? In other words, what is the kinematics of this gas? Is it flowing in? Is it flowing out? Is it floating around? And then the clumpiness. Smaller and smaller scale. It may not be, you say, in satellites, but can it be in small clumps? Is there evidence? I heard some evidence from other kind of work about clumpiness. And now the theoretical side, L-star galaxy is a borderline halo, if it's a central galaxy, for Werk shock heating. So it may have a hot halo with a stable shock, or it may not. It may have it in the future. This hot halo in the Werk shock is generated by some trigger, like a merger, a small merger. So many of those halos may not yet have hot halo. It's a borderline. Clumpiness. There are a lot of discussion in the past about little thermal instability kind of clumps within the hot halo of a second phase of cold gas. This may be it, like high velocity clouds. And so on.
So,
maybe cold outflows. You can push gas and cold gas out.
Okay, so a couple things. When you're talking about kinematics, do we see inflow or outflow? We really can't tell, right? We just have line of sight velocities, so it's very hard to distinguish those processes. Clumpiness, almost certainly the circumgalactic medium is clumpy to some degree. Determining the size of those clouds is actually very difficult. The density of the clouds, I will say, is quite low, and especially if you're going to put them in a hot halo, it turns out that these densities rule out almost unequivocally this model where cool clouds are condensing out of a hot medium. As far as how they relate to the high velocity clouds, it's my understanding that at least with the high velocity clouds, most of that stuff is detected within 10 kiloparsecs of our own galaxy's disk. That's very close in. We're looking at material, between 10 and 160 kiloparsecs. These aren't the same beasts. For how much mass is in these clumpy gas clouds that have a very high covering fraction, it's a lot. It's unavoidable how much it is. In a 10 to the 12.2 halo of virial mass 10 to the 12.2, you have anywhere between 7 and 12 times 10 to the 10, so almost 10 to the 11 solar masses of cool gas in these halos. But I do appreciate your point about cause halos probing the transition mass at which, and so, in the future, we'd like to look at more massive galaxies.
Okay, sorry. Anatoly, very, very quick.
Well, I actually, so I don't really know, but I do know that some people, Nicholas Lanier in particular, is working on observing the halo of Andromeda with the cosmic origin spectrograph to look at this kind of same halo gas that we're looking at. And I think his initial results are actually that there's a lot of gas there. That was my it's very new work. Yeah. Oh, right, but predominantly ionized hydrogen is what we're talking about. This hydrogen that we see in absorption has a column density of, say, neutral hydrogen of 10 to the 16. That's not detectable via emission. The total hydrogen columns of 10 to the 19, 10 to the 20 come about when you add in the ionized component, which is required because you see all of these various ionization states of metal lines. So you can do this ionization correction.
Okay, let's end there. We will come back here at 11:25. And we actually get a 25-minute coffee break because of my ruthlessness. You can all thank me later.